In 1957, a cartographer named Marie Tharp sat at a drafting table in a basement office at Columbia University, doing what she had done for years, plotting thousands of sonar depth readings onto paper, one by one, translating numbers into topography. She was not allowed on the research vessels that collected the data. She had never seen the ocean floor with her own eyes, but as she connected the data points into cross-sectional profiles of the Atlantic, something emerged that she had not expected. Running down the center of the Mid-Atlantic Ridge was a deep valley, a rift, slicing the ridge in two like a wound. Her colleague, Bruce Hizison, dismissed it at first. Girl talk, he called it. The implication of a rift valley, that the seafloor was pulling apart, that continents might actually be drifting, was, in the 1950s, geologically heretical. But the data kept saying the same thing. Profile after profile, from different latitudes and different expeditions, all converged on the same conclusion. Something fundamental was happening beneath the Atlantic, and it had been there all along, hidden under miles of black water, waiting for someone to notice. That is, in many ways, the quiet pattern behind nearly every great oceanic discovery. It rarely begins with ambition. It almost never starts with someone looking for something extraordinary. It begins with routine, a survey, a calibration, a mapping exercise, and then the data does something the instruments weren't supposed to find. The ocean covers roughly 71% of the Earth's surface, and yet, as of the most recent figures, only about 27% of the global seafloor has been mapped using modern high-resolution sonar. Less than 1,000% of the deep ocean floor has been directly observed by human eyes or cameras. We have better topographical maps of Mars and the Moon than we do of the terrain beneath our own seas. The deep ocean is not merely unexplored in the way a remote forest might be. It exists in a state closer to total darkness, physical, informational, conceptual. We do not know its shape in most places. We do not know what rests on it. And when we do go looking, what we find frequently challenges the assumptions we carried down with us. Consider what happened in February of 1977 at the Galápagos Rift. A team of geologists from Oregon State University and the Woods Hole Oceanographic Institution descended in the deep-sea submersible Alvin to a section of the Pacific seafloor roughly 2,500 meters below the surface. The expedition's purpose was narrowly defined: to investigate thermal anomalies that had been detected during earlier towed camera surveys. The scientists expected to find warm water seeping from the seafloor. What they found instead was a landscape that seemed to belong to another planet. Jets of superheated water, some exceeding 300 degrees Celsius, roared from chimney-like structures on the ocean floor. Surrounding these hydrothermal vents were dense colonies of organisms that had never been seen before, giant tube worms with no mouth, no gut, and no anus, surviving entirely on bacteria that fed on hydrogen sulfide. Ghostly white crabs picked their way across mineral deposits. Mussels clustered in the warm zones. The entire ecosystem had no dependence on sunlight whatsoever. This discovery didn't just add a new species to the record. It shattered a foundational assumption of biology, that all complex life on Earth ultimately depended on photosynthesis. The finding was accidental in the most precise sense. The scientists had gone looking for warm water. They found an entirely new model for how life could exist. This dynamic routine survey yields radical discovery, has repeated itself across decades, across oceans, and across scientific disciplines. It has revealed not only new species and lost ships, but hidden structures deep within the planet itself. Structures that are rewriting our understanding of how Earth formed and how it continues to evolve. In September of 2024, a team of geologists from the University of Maryland published a finding that drew remarkably little public attention given its significance. Led by postdoctoral researcher Jingchuan Wang, the group had been analyzing seismic wave data from the East Pacific Rise, a tectonic plate boundary on the floor of the southeastern Pacific Ocean. Seismic imaging works on a principle not unlike medical CT scanning. By tracking how waves travel through different materials at different speeds, scientists can construct a cross-sectional picture of the Earth's interior. Wang's team was studying the mantle transition zone, a region located between 410 and 660 kilometers below the Earth's surface, when they noticed something anomalous. In one section, the transition zone was unusually thick. The seismic waves were moving through it at roughly half the speed predicted by existing models. Wang and his colleagues concluded was that they were looking at the remnant of an ancient piece of seafloor, a slab of oceanic crust that had been subducted into the Earth's mantle roughly 250 million years ago during the age of the dinosaurs, and had never fully descended to the core. It had become lodged in the transition zone, sinking far more slowly than theory suggested was possible. In their words, it was a fossilized fingerprint of a geological process that had been operating on a scale and timescale previously unappreciated. The findings suggested that the mantle transition zone could act as a kind of barrier, slowing or trapping descending material, and that the deep Earth might be littered with such ancient fragments, ghosts of former ocean floors embedded in the planet's interior, still influencing geological activity at the surface. This kind of discovery reveals something important about how science advances in practice. The team was not looking for an ancient seafloor, they were conducting what amounted to a mapping exercise. The anomaly surfaced through careful, systematic analysis of data that had been collected for broader purposes, and it opened a line of inquiry with implications stretching from plate tectonics to planetary science. The same principle applied to a discovery announced in 2014 by a team led by mineralogist Steve Jacobson at Northwestern University. Jacobson had spent years in his laboratory synthesizing ringwoodite, a high-pressure mineral found in the transition zone, and testing how much water its crystal structure could absorb. Around the same time, geologist Graham Pearson at the University of Alberta had been examining a batch of low-quality diamonds purchased from river pannas near the town of Juína in western Brazil. These diamonds were rough, dark, battered, commercially worthless, but diamonds form deep in the mantle, and as they crystallize under enormous heat and pressure, they can trap tiny inclusions of the minerals surrounding them. They are, in effect, sealed capsules from the deep earth. Inside one of Pearson's Brazilian diamonds, he and his colleagues found a speck of ringwoodite, and it was hydrated, containing roughly 1% water by weight. This single inclusion, smaller than a grain of sand, carried a staggering implication. If the ringwoodite in the mantle transition zone contained water at even moderate concentrations, the total volume could amount to several times the water in all of Earth's surface oceans combined. Jacobson's lab work and seismic data from collaborator Brandon Schmant at the University of New Mexico supported the plausibility. Beneath North America, they found seismic evidence consistent with water-bearing minerals melting just below the transition zone, forming pools of molten rock that slowed incoming seismic waves in a distinctive pattern. The idea was extraordinary, a hidden reservoir of water, not pooled as a subterranean sea, but locked molecule by molecule inside the crystal lattice of minerals under crushing pressure, hundreds of kilometers beneath the surface. It was not an ocean in any visual sense. There was no cavern, no darkness full of water. And yet, the quantity of water suggested by even conservative estimates was vast enough to reshape fundamental questions about where Earth's water came from and how the planet has maintained habitable conditions over billions of years. This is the paradox of oceanic and deep Earth research. The more routine the method, the more revolutionary the result can be. No one went to Brazil to discover a hidden ocean. They went to buy cheap diamonds. No one aimed a sonar pulse at the East Pacific Rise expecting to find a 250 million-year-old slab of fossilized seafloor. They were running seismic profiles, and when a French Navy underwater drone was patrolling the waters off Saint-Tropez in early March of 2025, scanning the seabed as part of a government project to monitor deep-sea resources and infrastructure like undersea cables, no one aboard was thinking about the Renaissance. The drone sonar pinged something large. The operators sent it back with cameras. Then they sent a robotic submersible with high-definition imaging. What they found, sitting 2,567 meters below the surface, was the wreck of a ship that appeared to date from the 16th century. It was intact to a degree that stunned the archaeologists who reviewed the footage. 200 ceramic jugs with pinched spouts, many marked with the monogram IHS, the first three letters of the Greek name of Jesus, lay in ordered rows. Around 100 yellow plates were stacked nearby. There were cauldrons, an anchor, 6 cannons and bars of metal that appeared to be trade goods. Analysis of the ceramics pointed to the Liguria region of northern Italy. The vessel, dubbed Camarat 4, was almost certainly a merchant ship, lost nearly 500 years ago on what may have been a trading run along the Mediterranean coast. It was, at the time of discovery, the deepest shipwreck ever found in French territorial waters. What made the preservation so remarkable was the depth itself. At 2,567 meters, the The wreck lay far beyond the reach of any salvage operation, any diver, any anchor drag. Human debris, a soda can, an empty yogurt container had drifted down to the site, but no human hand had touched the cargo since it sank. The archaeologist Marine Sedania described it as frozen in time. The research team plans to construct a full three-dimensional digital model of the ship over the coming years, extracting samples by remote submersible. Each of these discoveries, the Rift Valley mapped by Tharp, the hydrothermal vents found at the Galápagos, the ancient slab detected beneath the Pacific, the hidden reservoir inferred from a flawed diamond, the Renaissance merchant ship found by a military drone emerged not from some grand expedition mounted in search of the unknown, but from the accumulated weight of ordinary work. Survey lines run, sonar pulses sent, depth readings plotted, data reviewed, and then, in the noise, a signal that didn't fit. There is a tendency when we tell stories of discovery to frame them as moments of sudden revelation, as if the ocean yields its secrets in dramatic bursts. The reality is almost always quieter. The signal emerges slowly, often ambiguously, and it is recognized only by people who know what the expected data should look like and are disciplined enough to take the anomaly seriously when it appears. He's dismissed Tharp's Rift Valley for months. Jacobson spent years synthesizing minerals in a lab before a diamond from Brazil confirmed what his experiments predicted. The French Navy drone had no idea it was looking at a shipwreck until someone decided to investigate an irregular sonar return. What the ocean conceals, it conceals totally. There is no partial visibility at depth. No satellite can photograph a wreck at 2,500 meters. No telescope can peer through the mantle to see the remnants of a subducted plate. The only way to know what is down there is to go, with sound, with pressure, with instruments calibrated to detect the faintest departure from expectation. And this is precisely why the most transformative findings so often arise from the most routine operations. The extraordinary is invisible until someone turns on a machine for an ordinary purpose and watches as the screen shows something that shouldn't be there. More than 70% of the planet remains, in this sense, unrid. The deep ocean floor, the mantle beneath it, the structures and histories preserved in sediment and mineral and wreckage. All of it persists in silence, untouched by light, unobserved by any instrument, waiting in the particular patience of geological time. The surveys continue. The sonar pulses travel outward and return, and sometimes in the returning echo, there is a shape no one predicted. The outline of something buried, something ancient, something that changes what we thought we already knew about the ground beneath the water and the water beneath the ground.